In this video, we're going to introduce the idea of an improper integral of type 2. We've already seen how to use limits to deal with improper integrals of type 1, which are improper integrals over an infinite domain, such as an integral from 0 to infinity or from negative infinity to 0. In this video, we turn our attention to improper integrals of type 2, which are ones which have an infinite range instead of an infinite domain. We're going to focus on how we can use limits to evaluate these types of integrals in an analogous way to how we use them to evaluate type 1 integrals. A standard feature of type 2 improper integrals is of a function that has a discontinuity between the endpoints of integration where we have a vertical asymptote. So to get an idea of why this could be a problem, let's take a look at the following example. So let's say we wanted to evaluate the integral from -1 to 1 of 1 over x squared dx. At first glance, there doesn't seem to be anything odd going on with this integral. We have a nice function, 1 over x squared, whose antiderivative we can find using the power rule, and we're evaluating it from a finite number -1 to another finite number 1. However, if we take a look at the graph of the function, which is shown here on the top right-hand corner, we see that we do have something odd going on after all. In fact, this graph has a vertical asymptote at x equals 0, at the y-axis. And so here, if we're going from integrating from -1 to 1, this range would actually include that entire y-axis where we have that asymptote. And so we have sort of an infinite range there where the graphs will shoot up arbitrarily high, approaching the x equals 0 from both sides. And so what we notice in particular is that 1 over x squared, our integrand, is not defined at x equals 0, which is right in the middle of our interval for our integral. It's right between -1 and 1. And so this is exactly the type of problem that we might come across with improper integrals of type 2. Where we have an infinite range. Now we could try using the fundamental theorem of calculus, just like we would in almost any other case, and see if it works here. So here we would have the integral from -1 to 1, and I'm going to rewrite this as x to the -2nd power so that we can use the power rule right away. The fundamental theorem of calculus says we want to find an antiderivative for this function, and so that's going to be -x to the -1, and then evaluated from -1 to 1. And of course, this is going to be just -1 over x from -1 to 1. This will be a little bit easier to evaluate. When we substitute in 1, I just get -1 over 1, which is -1. And I'm going to subtract from that -1 over -1, which is +1. And so we get -1 minus 1, which is -2. And so it looks like, if we didn't really think about this integral, it looks like we would be able to get a value for our integral of -2. However, this is a huge problem. If we come back to our graph at the top, we can notice that this graph is always positive. Our function's always positive from -1 to 1, and therefore this definite integral should be computing the area under the curve of our function from -1 to 1. And so since all of that area is above the x-axis, this integral should be positive, should give us a positive value for that area. And as we see here, the value that we get using the fundamental theorem of calculus is -2. It's not a positive number. And so this tells us that when we have vertical asymptotes and infinite range in our interval that we're integrating over, we do have to do something else. We can't just use the fundamental theorem of calculus like we have before. And so this is where improper integrals of type 2 come into play, and where we can use limits to evaluate these types of integrals. So in order to see how limits can be used to evaluate these types of improper integrals, let's simplify our integral just a little bit. Instead of considering the entire integral from -1 to 1 of 1 over x squared, let's just look at half of that. Namely, let's consider the integral from 0 to 1 of 1 over x squared dx. Notice this still has an infinite range problem because the lower limit of integration here, 0, is the location of our vertical asymptote. This integral from 0 to 1 of 1 over x squared should consider the area. It should compute the area from x equals 0 to x equal 1. And we will have this sort of infinite sliver of area that's going to go up between the y-axis and our curve as the curve gets closer and closer to 0. If we want to evaluate this integral properly, one way we could do that is to pick some value of c between 0 and 1. And it can be any number we want, any arbitrary number between 0 and 1. And we could instead consider what's happening from x equals c to x equal 1. And so if we want, we can consider this area here that's shaded in blue. And this would be given by the definite integral c to 1 of our function, 1 over x squared dx. And this integral gives us no issues whatsoever in computation because there's no infinite range from c to 1. We have a standard definite integral, and so we can use the fundamental theorem of calculus to compute this definite integral. Ultimately, though, what we want is the integral starting at 0. We want all of that area. And so what we can do is we can think about this as dragging c closer and closer to the y-axis. In other words, we want to take the limit as c gets closer and closer to 0. However, since our integral here starts at x equals 0, we don't want c to be smaller than 0. We only want c to be able to approach 0 from the right or from the positive direction. And so we will actually want to consider a one-sided limit here. We want to take the limit as c goes to 0 from the right. And you can see in the picture that this is exactly what we want to be doing. And as that c is dragged closer and closer to the y-axis, the blue area gets closer and closer to giving us all of the red area. And so by actually taking the limit of this value, we will get the exact value. And so in this case, we can define the integral from 0 to 1 of 1 over x squared dx to be the limit as c goes to 0 from the right of the definite integral from c to 1 of 1 over x squared dx. And we can compute this integral and then take the limit, just like we did with improper integrals of type 1, and find our value for this integral. So this example will give us a model for the definition of an improper integral where the discontinuity and vertical asymptote lie in the lower limit of integration. And we can make slight modifications to see what will happen if the discontinuity happens at our upper limit of integration or at some other point between the two limits of integration. So here we have formal definitions for the three varieties of improper integrals of type 2. Our first definition says that if f of x is discontinuous at our lower limit a, then the integral from a to b of f is going to equal the integral from c to b of f, and then the limit as c approaches a from the right. Now notice that this is a direct generalization of the example that we just considered, where we had our function 1 over x squared that was discontinuous at the lower limit of 0, and we were able to define that integral by taking the limit as c goes to 0 from the right of the integral from 0 to 1 of our function 1 over x squared. And so this first definition is dealing with the general case of what happens when we have that discontinuity at our lower limit. And the solution is always to take the limit as c goes to that x value for the discontinuity from the right and take the indefinite integral from c to our original upper limit. In our second case, we consider what happens if we have a discontinuity at the upper limit or on the right side of our region. In that case, we're going to replace the upper limit of our integral with c. So we have the definite integral from a to c of f of x. And then we're going to take the limit as c gets closer and closer to b. But here, c is going to be smaller than b because we want c to be between a and b. And so that means we want to have c approach b from the left or from below. And so our integral from a to b of f, in this case, is the limit as c approaches b from the left of the integral from a to c of f of x dx. In our third case, we consider what happens when the discontinuity is at some point between our limits of integration, so somewhere between a and b. And in that case, we're going to break up our integral from a to b into two other integrals. The first will be from a to d, and this integral will be like our second one here, where we have a discontinuity at the upper limit. And our second integral is the integral from d to b of f of x, and this will be like our first integral, our first type. And so although it doesn't appear to be the case in our third definition here, we do actually need to compute two limits and add them together in order to evaluate this type of improper integral, since each of our two integrals that we're adding together to get our given integral will be defined in terms of the appropriate limits above. So to ensure that we have a good understanding about what these definitions say, let's consider the following three integrals and rewrite all of them in terms of limits of definite integrals. Our first integral is the integral from 0 to 1 of 1 over x dx. We think about the function 1 over x, and we see that it's going to have a discontinuity at 0, which is our lower limit of integration. In such cases, we're going to first compute the definite integral from c to 1 of our function, in this case 1 over x dx. And then we're going to drag this value of c, that variable c, we're going to drag it closer and closer to the original limit, which is 0. But we always want to pick c to be bigger than 0 in this case, so we want to pick c going to 0 from the right, because we want c to be some value between 0 and 1. And so we have the limit as c goes to 0 from the right of the integral from c to 1 of 1 over x dx. Our second integral is the integral from 5 to 8 of 1 over the quantity x minus 8 squared dx. By looking at our function here, we see that it's going to be 0 at x equal to 8 and x equal to 8 only, and that happens to be our upper limit of integration here. And so in order to handle this particular case, we're going to consider the integral from 5, our original lower limit, to an arbitrary upper limit of c of our function, 1 over x minus 8 quantity squared dx. And this definite integral is perfectly fine, since the function will be defined from 5 to c. And now we want to take the limit by thinking of what happens when we drag c closer and closer to 8. So we want the limit of c goes to 8, but because c is going to be a number between 5 and 8, it's going to be smaller than 8. And so we only want to consider the limit as c goes to 8 from the left. And so we have a one-sided limit here as c goes to 8 from the left of the integral of 5 to c of 1 over quantity x minus 8 squared dx. Our third integral is the integral from 1 to 5 of 1 over x minus 2 dx. And when we look at this function, we notice that it has a discontinuity at x equal to 2. That'll give us a denominator of 0 and an undefined function. And notice that 2 is between 1 and 5. So this is in our interval that we're considering here for the integral. And so we want to rewrite this as two integrals. We want to rewrite this as the integral from 1 to 2 of 1 over x minus 2 dx, plus the integral from 2 to 5 of 1 over x minus 2 dx. And now each of these two integrals can be rewritten in terms of limits. So if you'd like to try to do these on your own, pause the video, and when you're ready, resume the video to see how to rewrite each of these two integrals using limits. For the first integral from 1 to 2, we have a discontinuity at the upper limit of 2, and so we have the limit as c approaches 2 from the left of the integral 1 to c of 1 over x minus 2 dx. And for the second integral from 2 to 5, we want to take the limit as c goes to 2 from the right of the integral from c to 5 of 1 over x minus 2 dx.